Welcome back. We're going to begin studying chemical reactions and material balances in this lesson. So in this video, we're going to just discuss some terminology. We really want to talk about stoichiometry. You've learned about stoichiometry in a chemistry class, so balancing chemical reactions is probably not a big deal anymore. But that's the basis for everything that we will be doing with reactions. So here we have a chemical reaction, SO2 and oxygen producing SO3. In order for this to be a balanced equation, it requires two SO2 molecules plus an O2 to make two SO3 molecules. Now we typically, in a chemistry class in particular, make sure that these are always whole numbers. We will, in the future in chemical engineering, sometimes relax those rules, but whole numbers at least physically make sense. Two molecules of SO2, one molecule of O2 have to get together and they will play mix and match parts and come back as two new molecules. Now those stoichiometric coefficients are telling us ratios of how much of various chemicals will be produced or will be involved in the reaction. So for instance, the 2 in front of SO2 tells me that there's going to be 2 molecules of SO2 consumed in this reaction the way it's written. And there's 1 in front of the O2, so therefore for every 2 moles of SO2 consumed, 1 mole of oxygen will also be consumed. Or for 1 mole of oxygen consumed, there will be 2 moles of SO3 generated. Or any other combination that you might come up with. We are going to want to talk about whether or not things are being fed into the reactor in stoichiometric ratio or stoichiometric proportion. So the easiest way to do this is look at all of the reactants. Okay, I need 2 moles of SO2 and 1 mole of O2. That means I need 3 molecules for this reaction to happen. 2 of those 3 need to be SO2, so therefore 2/3 or 0.67 is going to be the required mole fraction of SO2 in the feed for stoichiometric proportion. O2, of those 3 molecules, I need 1 to be oxygen, and so therefore 1/3 is going to be oxygen for stoichiometric proportion. Now we don't always do our feeds in stoichiometric proportion. Often there's very good reasons for why we might do that, but we want to be able to quantify when things are not fed stoichiometrically. One reactant will run out before the other one. The reactant that would run out first is going to be called the limiting reactant. The other one is going to still have some left over at the end. That will be called the excess reactant. One of the ways that mathematically you can identify the limiting reactant is by comparing the mole fraction that you would have for stoichiometric proportion to the actual mole fraction. If the limiting reactant mole fraction, the actual mole fraction, is smaller than the stoichiometric required mole fraction, then that is the limiting reactant. If the actual mole fraction is larger, then it's an excess reactant. So for instance, let's look back at this little chemical reaction. SO2 plus O2 makes SO3. If we have a feed of 50% SO2 and O2, we want to know what's the limiting reactant there. Or if we change it to where we have 25% oxygen and 75% SO2, what is the limiting reactant? So we want to recall that the stoichiometric feed was 2/3 SO2 and 1/3 O2. If I have 50% SO2, then for SO2, 0.5 is the actual feed composition, 0.67 is the stoichiometric feed composition. 0.5 is less, and so therefore SO2 is the limiting reactant. O2 would be the excess. For the other example, 25% oxygen and 75% SO2. Now you can choose to look at the O2 or the SO2, doesn't matter. 75% SO2 is the actual. The stoichiometric proportion is 2/3. 75% is greater than 67%, so SO2 is the excess reactant in this particular case. One last thing that we want to be able to define before we move on is fractional excess. We want to say how much extra do I have, okay? So if I let N sub F be the number of moles of the excess reactant, we only define this for excess, not for the one that is the limiting reactant. So if NF is the excess reactant moles, NS is the number of moles that would be required if it were in stoichiometric proportion. The definition of fractional excess is the amount in the feed minus the amount for stoichiometry divided by the amount for stoichiometry is fractional excess. But if you were to divide all of those terms, just numerator and denominator, by the total number of moles, this could be converted to mole fractions. Now it is very key to recall that this is a mole fraction, okay? This only works for mole fractions. So the mole fraction in the feed minus the stoichiometric mole fraction divided by the total mole fraction. So let's look at those two previous problems and determine the fractional excess. In the first example, O2 was the one in excess. The system was 50% SO2, meaning it was also 50% SO2. The stoichiometric feed for O2 was 0.33. So 0.5 minus 0.33 divided by 0.33 is 1/2. So we had 50% excess, 50% more than what we actually required. In the second example, SO2 was in excess. So I'll apply these definitions to the mole fractions of SO2. The feed was 75% SO2. The stoichiometric requirement was 0.67. 0.75 minus 0.67 divided by 0.67, 12.5% excess. In the next video, we'll talk about reactions, how close they come to being complete, and the terminology that we'll use associated with that.